idea of colligative properties. Colligative properties are neat because what's special about them is it only matters how much is dissolved, not what's dissolved. All right, so we just want to know how many particles are in here. So I've got a couple of different ones. I've got so normally we look at things. We look at the boiling point, so boiling point, and the melting point. And interesting thing happens. The boiling point goes up, and the melting point goes down. Now, vapor pressure is related to the boiling point. It's the pressure above a gas. It also goes up, all right? And so these are kind of related. And so let's play with the boiling point. Let's figure out what we mean by vapor pressure and boiling point. So this is the effects we're going to be seeing. So let's look at, let's make a beaker here containing some water. So I've got these molecules of water. And as I warm this up, the molecules of water, they're bouncing around. And occasionally, one gets up enough speed to overcome all the attractive forces between it and the other molecules of water around it, and it leaves out into the gas phase. All right? And so, constantly getting these up, and that's called the vapor pressure. Alright, now that vapor pressure, if I raise the temperature, then I raise the distribution, the average kinetic energy of each molecule, and so more of them are likely to make it into the gas phase, and so we would raise this pressure. Now, at every temperature, I have a little bit of vapor pressure. Right? This is why we get evaporation. Is that the wind comes by, it moves some of that water, and so then it tries to replace it, and there's more space for that vapor pressure. Vapor pressure of water in particular is only dependent on temperature. So raise the temperature, it goes up, lower it, it goes down. See how easy that is? Alright, now what if I take a similar thing, but now I've got some particles dissolved in it. Now I have, I don't know, some sodium in there or some chlorine. It doesn't matter what it is. Some of this water can make it up and go into the gas phase. Some of it will hit and bounce off. And if it bounces off, it lowers the vapor pressure. All right? And so as I lower that pressure, then I have to raise the temperature to get it up to even higher. Now, a special thing happens when the vapor pressure equals atmospheric pressure. You know, the pressure above here, or out here outside this container, when those are equal, that's the boiling point. That means if we want something to boil faster, we can lower the atmospheric pressure around it. We can use it in a vacuum, and it'll boil faster. Or we can use a pressure cooker. If you close this container off and you build up pressure up there, then the liquid has to get to a higher temperature before it can boil. That means it's going to be hotter. If it's hot, it'll cook the food faster. So that's the idea behind a pressure cooker. Right? So we could raise this temperature by either raise the boiling point by either increasing the pressure, or we can add some solute in it. You've probably added some salt to your water. Let's say you're going to cook some spaghetti or something, and you want to boil some water, and you want it to cook pretty fast, and so you add some salt to your water, and it gets the water actually hotter before it boils. And that means when you throw in your food, it cooks faster because the water is at a higher temperature. All right. Okay. Now there's a limit to that, but for food, because you add too much salt, and then everything tastes too salty, and nobody's going to want to eat it. So that's why we have pressure cookers. All right. This idea of melting point, the same kind of idea. So when things decide to start freezing, what happens is the molecules are going to get lined up in a very orderly fashion, and they form crystals. But if I've got these particles in here, you can see that it's tougher for these things to get lined up. They have to kind of push everything out of the way. And so what happens, why do we use this, is we can throw, if I go outside and I've got ice all over my my porch, and I go, oh man, I can't go outside, it's too slippery. Oh, gotta stay home, cancel, can't make it to work today, sorry. But, oh no, I got someplace I actually want to go. I'm going to throw some salt out there. Now, the salt doesn't actually heat up the concrete. It doesn't melt the ice that way. The way it melts is it dissolves on the surface. And so that the top layer will have some salt dissolved in it. And we lower the melting point. Let's say it is 30 degrees Fahrenheit outside. So it's lower than the boiling point, I mean the melting point of my 32 for ice. Alright? But if I lower the melting point by adding some salt below whatever temperature it is outside, then it'll melt. Alright? It's warm enough to melt. So you add that ice, it depresses that melting point, and it causes everything to melt. There's a limit to how far down we can depress it, and the reason we use salt on our roads, especially, is because don't forget, salt splits. When we mix that in water, it dissociates, and so we actually get this 2 for 1. We get 2 particles for each formula unit of salt. Alright, so that's why we like to use salt on our roads. So we add it out onto the roads, causes everything to melt. Now, why is it a problem? Well, it gets down in the cracks, and then as the water evaporates, it leaves behind the salt, and it forms these the crystals, and it spreads out any cracks that were in the road, causing potholes and the road to crack. Salt flows off to the side of the road as it melts. It gets down into the soil, kills off all the grass and the flowers, and so it's just not a good situation. And then you might have been told never buy a used car from up north, right? And the reason for that is all the salt that they use in the winter that gets up under their car, and then the salt is an electrolyte, and so it leads to rusting. So rusting takes you have to have an electrolyte solution. So if you hit your car with deionized water with no ions in it, it's not gonna rust. But if you hit it with the salt water, it rusts pretty quickly. All right. Now this is colligative property. It doesn't have to be salt. Now, what's nice is it's got this 2 for 1. But what if we had something that was cheap? All right, it has to be pretty cheap because we're going to use a lot of it. We use a lot of salt every year just for our roads. It would be nice if it didn't dissociate and make an electrolyte solution. So let's make something that's not going to be ionic then, so it won't be an electrolyte. Let's make something then that won't kill the grass. And so they found a compound, and the compound that they chose to test was urea. Now, urea is nice. It's a covalent compound. It's a fertilizer for grass. It doesn't cause the cars to rust. It worked great, and you get it. You go up to any farm, and if you bring your own bucket, they'll let you have as much urea as you can carry. All right. Now, where's urea found? Well, it's found in urine, and this worked wonderful. They tested it on the roads. It didn't cause all the damage to the roads. Didn't cause damage to the cars. And in spring, you never saw such pretty flowers on the side of these roads. They were great. So they tried it a couple of years, and then they quit doing it. And the reason they quit doing it really came down to nobody wanted to drive down the P road. You know, you roll the window down and you get out, something smells, and it was really just the smell. All right, and so they're still looking for other alternatives, um, and so we're still using salt. We occasionally put sand down, and it's more for traction. It doesn't dissolve, so it isn't going to be a colligative property. It's just going to give us a little more traction. All right, but to actually melt everything, we need it to dissolve, and so salt is really powerful. So let's look at our other ideas. Here we've got osmotic pressure, the pressure across the membrane. So most of you have studied osmosis. I'm gonna leave you to look at that. One thing real common there is it looks just like the ideal gas law. Let me show that real quick. So osmotic pressure. Oh, look at this. This is capital P. That's osmotic pressure, just as a so capital Pi. So do it just as if you find this, but you got to dissociate all the ions. All right. So when you do N, it's got to be all the ions. Let's see. The last thing we have is this idea of equivalence. Now, equivalence, you're going to take the charge times the molarity. And that'll give you equivalence per liter. All right. So if I have 3 molar NaCl, I have to be careful because I need to dissociate. So that's 3 molar Na and 3 molar Cl. And so when we do this, you're just taking the magnitude of the charge. And so this would be 6 equivalents per liter. All right. So you have to be careful. So usually we'll ask you stuff like, I've got 2 moles per liter of, let's do calcium plus 2. All right, and so that would be 2 times the plus 2. That would be 4 equivalents per liter. All right, so that comes into play when we're doing a lot of our osmosis, and we use equivalents on a couple of problems in the book, but really what I care about there is just doing this calculation. So when you're doing these, you're really looking for the terms dissolved in or is dissolved in. You've got to identify what's the solution, and what's the solvent. Okay, so once you're able to do those, this chapter should not too bad. So we'll catch you on the next one. Maybe we'll work a few practice problems of this if students start to struggle with it. But try some. As long as you identify that, it shouldn't be too much trouble.